Hello everybody. Once again I am here for the new session for your solid state physics paper number 13A. Myself again Dr. S.D. Chavan, Department of Physics, Adarsh College, Hingoli. So in the previous session we have seen what exactly the symmetry operations are to be there and how they are showing or the whatever be the lattice is going to be there, they are having some symmetry is going to be followed around one point. Now let's see what exactly we have seen, and today what we are going to see regarding the next point. So in the symmetry operations we have seen simply nothing but to be a your transfer itself, the what type of the symmetry is going to be there, that is nothing but to be showing you what type of the crystal it is going to be transforming, that particular structure is going to there in that lattice is to be there or crystal. Now we have seen the symmetry operations are basically having the four types of the symmetry operations are there. First one is to be your translation, rotation, reflection, inversion. These are the four symmetry operations are going to be there. In this we have already discussed in detail that what is translation, what is rotation, some sort of reflection. We have little bit detail that if we missed, I will just revise it what exactly meaning to be as an reflection. As the reflection we already seen that it is nothing but to be a whenever the two sections done by the line symmetry or the plane of that symmetry, that time whatever be the 2 points are going to be formed, basically it is nothing but to be a reflection. And the reflection is somehow likewise this one, as the plane is represented by the m. And if you look at here in this case, this is what the case where the already we have seen in detail also. Let's revise it. So this type of the plane when drawn from the center of the axis, then it will give you two equal halves which are looks like to be a your mirror images, and that is what nothing but to be a reflection symmetry. In that we have seen 10 point groups are going to be formed, groups of the 10 point groups are going to be possible. As we are aware about that the reflection is nothing but to be of the two cases are going to be there, either the rotation is also to be there and the reflection, that is to be two equal halves are going to be formed. Now here the 10 point groups are the possible number of in the two dimensional lattices are going to be concerned. That possible number of reflections is nothing but to be rotation with the reflection, both the things are somehow the combination symmetry is going to be there. And in this case we have seen the 10 point groups are possible in the two dimensional cases are concerned. Now in this case if you look at these 1 m, 2 mm, 3 m, 4 mm, 6 mm, these are the 10 point groups are going to be there possible in the two dimensional. Now here this reflection symmetry when we are going to see in detail, this first m is nothing but to be showing you what exactly this representation for the line or the plane which cuts that from the center of the axis, or that will use you the reflection symmetry, that two equal halves are going to be formed which looks like to be mirror images of each other. Now second, what exactly this m is going to be there, for to understand this what is mean by to be this second m is going to be there, for that we have to see a little bit next part, and that we have seen the 10 point groups, that we will see in detail what exactly that is going to be there. So why there is not possible to be as an 1m, and where there is sometimes you have seen there is 2m is 2m's are there. Now in this case the as the 2m part comes, that time we will see in detail. Here if you look at this case where the first one and the 1m symmetry or the two dimensional point groups are going to be there, in this part where if you look at this case, if you see this, here is the one, that case where there is no possible of the line passing or the plane pass through it, which will gives you completely two reflected or the two mirror images are going to be there. But if you look at this 1m, and if there is this one is the center point here, and if I draw one line which is passing through this center, and that will give me exactly line or we can say plane passing through that. Now this will give me two equal halves, this one and this one is going to be there. and these two equal halves are nothing but to be mirror images of each other. One will be mirror for another, another will be looks like to be mirror for the first one. So this is what the case where it is to as an reflection symmetry part is going to be there, as far as this 1 and the 1m is going to be concerned. Now where it is not possible to be as an here, why there is not another m is going to be there? Because second m is nothing but to be, it gives you when there is possibility of another axis which is perpendicular to this plane or the line, then in that case the second m comes. That is nothing but to be, the second m is not possible here because it is not giving me, if I am drawing the another, if this one is the first m or the particularly your line or plane passing through this axis, but if I draw forcefully second line or perpendicular to this second m, that is nothing but to be representation in this reflection symmetry, then it will not give me the two equal halves, and that's why the second m is not possible in this case. Now if you look at the another case where it is to be as an second example where it is to be as an point group is going to be there, here it is quite interesting to understand why there is 2m possibles and the 1m is not possible is to be there. So here again this second, that is to be as in two nodes are to be, two rotations are going to be there, but the reflection is not going to be possible. As I am trying to draw any line of the axis or the plane through this axis, then it will not give me any way that two equal halves are there, or in this way also. So this is not possible here in this case. But here if you look at in this case, why there is first m is representation for the case where it gives me a line which is passing through this particular case along the particular symmetry, and that is nothing but to be giving me two equal halves. Here is the one and here is the another. And if I am drawing another line or which is another plane, and that another plane is perpendicular to this center of the axis symmetry, so that time also it will give me two equal halves. If you look at this case, this is what the first m is to be there, that means the line passing through the through the axis, and which gives me equal halves which are mirror images of each other. And again I am drawing one another line which is perpendicular to the center of the axis, that time it again gives me the equal halves, and that is nothing but to be your another m is representation is to be there. So why there is 2mm possible? Because if I am drawing another perpendicular line perpendicular to this axis, then again it will gives me two equal halves or mirror images, and that's why the second m is going to be possible, and that's why it is written as a 2mm. Why every time there is somewhere 1m is to be written and somewhere it is written 2mm? It is not for the good look or something is going to be interesting to look. It is because of having some relationship as far as the this part where it is to be as an equal halves are not going to be possible, then another m is not going to be possible, as you are drawing perpendicular line or the plane to that center of the axis is going to be there, or the line of the symmetry you can say. Now this is what the another 2 and 2mm possible point groups are to be there. Another is to be as an another 2 point groups which are related with the 3 and 3m, and in this case also if you now here in this 3 there is no possible of the plane is gives you the two equal halves. But here if you look at this in 3m, if I draw from this way, it will gives me two equal halves. This is 1, this is 2. This is the one case. It is not necessary I should draw through this way also. I can draw the another way also. I can draw in this way also. If you draw this as an this axis through this way, it will also gives me two equal halves. Look at this. If I am drawing the another way, I will also get the another two equal halves. If you look at this, this is what the case, and I will get the two equal halves. But there is again another m is not possible here, because if I am trying to perpendicular to this, if I am trying another m, if I am trying to perpendicular to this axis, it will not give me, see suppose this is what the perpendicular, it will not give me two equal halves. This and this will be not be equal, and that's why only one m is to be there, and that's why this 3m is going to be there. So as far as the another point groups are to be there, this is all about the two dimensional we are discussing. So this is what another one example, or the another 2 points which are 4 and 4 mm. Here if you look at, this is one line plane of the axis which gives me 2 equal halves. This and this one is equal. Again I am drawing perpendicular to this axis, I will also get the similar equal halves again, and that's why the another m is going to be possible in this case. That's what the 4 and 4 mm is going to be possible. And if you look at another case where it is to be as an 2-dimensional point groups, there is to be as an 6 and 6 mm. Here you can draw in this way, or similarly, this is what the case where it is to be, I can draw this way, or if I will draw perpendicular to this, it is also gives me 2 equal halves. So in this way the 2-dimensional or the point groups are nothing but to be, or the reflection symmetries are going to be in this fashions are to be there. So this is what the reflection symmetries, 10 point groups are to be shown in this case. Now again related with that, we have seen in detail also what is going to be as an inversion meaning to be there, and inversion symmetry is going to be possible only in the 3-dimensional case, because in the 2-dimensional case there is no inversion symmetry is going to be possible as far as r point is going to be generated, and reverse to this at minus r point is not going to be possible in the 2-dimensional case. And that's why this type of the symmetry operation is only possible in the 3-dimensional case. As far as these are the 4 symmetry operations we have seen in detail. Now as using these symmetry operations, if you look at either rotation, reflection, or the translation or the inversion, all these symmetries are around some one point, and that will the generation of the your basically called as a point group is to be there. That means if whatever be the rotations or the whatever be the symmetry operations, if you look at all the symmetry operations are at certain point, they are these all groups of the symmetry operations are at one point. The rotation it gives you at certain point, the reflection at certain point to this way. So this is what exactly the generation for the your point group is to be there, at which point this symmetry is going to be followed, or that point, and what type of the symmetry is going to be, points are going to be followed. That group of the symmetry operations at one point is nothing but to be your point group is to be there. And in this point group, as far as again for the 2-dimensional and the 3-dimensional, we can also point out how many possible point groups are going to be there. As far as the 2-dimensional case is to be there, we already seen in detail that 10 point groups are going to be possible. As far as the in the reflection symmetry also we have seen in detail also that how this 1 m, 2 mm, 3 m, 4 mm, 6 mm, these are the 10 point groups which are possible as good as whatever the symmetry is going to be there, or as the symmetry operations are going to be followed at one point is to be there. But as far as the 3-dimensional case is to be there, it in this case, as the 3-dimensional case, it also increases the dimension also, and the another vector is going to be added, third vector is also going to be added. In that case the points are going to be increasing, and that's why the group of points are also going to be increasing. That means at one point whatever be the symmetry is going to be followed, that symmetry at that point, whatever be the collection of the point of the groups, that is also going to be increasing. And that's why in the 3-dimensional case the point group, possible point groups are 32. Now again, these suppose if the lattice is going to be formed with the consistent with these point groups, then such type of the lattices are called to be as your Bravais lattice. Now this is what the scientists work for this case. Now very important factor is which are the Bravais lattices. There are number of lattices are to be there, but Bravais lattices are those lattices which follows particularly point group. That means the lattice which consistent with your point group, that type of the lattices are nothing but to be called Bravais lattices. No doubt there are two type of the lattice, that means to be 2-dimensional and the 3-dimensional cases are to be there. Then again Bravais lattices are 2-dimensional and 3-dimensional cases are also to be there. So today we will see what exact these point groups are concerned to be there. So this is what exactly the point group meanings to be there. Now here what exactly the Bravais lattice, that is also we have seen. Now in this case we are moving forward to be as an, what is to be as an space group is to be there. As far as the space group is going to be concerned, so as we have seen, the point group is nothing but to be at one point, whatever the symmetry is going to be followed, that point, and whatever the points the symmetry are going to be followed at that point, that is nothing but to be your point groups are to be there, and that collection of that particular points are to be there. Points is nothing but to be here your atoms are going to be concerned. But now there is another part that is called to be as a space group. Now space group is the what, the group of all the elements of that whatever the symmetry in that crystal structure is to be there. Not only the symmetry points are going to be concerned, but whatever be the total points in that crystal structure followed with that particular symmetry is nothing but to be, that is all element with that group. That not only the symmetry followed points or the atoms, but also whatever be the elements of that crystals are going to be there, when they are going to be added, in that case whatever the group is going to be formed, or the point of group is going to be formed, that is nothing but to be called your space group is to be there. And no doubt here the point will definitely going to be increasing, that either we are not only taking the point surrounding that this symmetry is going to be followed, but we are considering the whatever the points in that element or the in that particular structure, crystal structure is going to be there, and due to that number of points are going to be increases as far as the space group is going to be concerned. And as far as the two-dimensional case is to be there, in this two-dimensional case, as far as the point groups are going to be space groups are going to be concerned, there are 17 space groups are possible. But as far as the three-dimensional case is going to be concerned, it also increases the number, that is 230 space groups are to be point groups are going to be possible. In this case it is to be as an your word is going to be used similarly, as in here it should be your space groups should be there. So this is all about the what the point groups and your space groups are going to be there. Now today we will see a little bit about the what exactly or what type of the your point groups are to be there, or the Bravais lattices in the two-dimensional cases are to be there. As we are aware about that, wherever the now this is what the case where we are looking forward to be as in types of the lattices are to be there. Now in this case, as far as the two-dimensional and the three-dimensional, these are the two parts we can bifurcate. As far as the two-dimensional case is going to be there, we are aware about that. As far as the part where it is to be as in two-dimensional cases are going to be there, here it is to be as in some sort of two-dimensional case. Here it is to be as an little bit mistake is to be there. Here it should be having the 10 point groups, and your 7 whatever be the point groups are going to be there, it is to be as an whatever be the your point groups should be there 10, and the space group should be 17. So here instead of point there should be a space, it should be there. So as far as the two-dimensional lattice are going to be concerned, the number of point groups are possible, that is 10, and the number of space groups are to be there, that is 17 are to be there. And in this case, when the Bravais lattice, which are the Bravais lattices we can call? We can say the Bravais lattices to those who followed, or those lattices which contains the point group. Those are following that point groups, that type of the lattices are nothing but to be called your basically Bravais lattices are to be there. And as far as the two-dimensional case is to be there, there are number of point groups are possible 10, and there are number of space groups are possible, that is 17, and there are 5 Bravais lattices are possible with these 10 point groups are to be there. And with that particular 5 Bravais lattices, the 4 crystal systems are going to be formed. Again, in the three-dimensional case is to be there, as far as the point groups are going to be concerned, it is 32 point groups are going to be possible. And as far as here it is not should be the point, it should be the space, and 230 space groups are going to be possible. Again, excuse me, there are with this 23 space groups or the 32 point groups, the whatever be the Bravais lattices are going to be formed, it is 14, and whatever be the crystal systems are going to be formed with that 14 Bravais lattices, are that is nothing but to be 7 crystal systems are going to be formed. Now in this case we are interested to find out what is to be as an two-dimensional or the Bravais lattices are to be there. As we are aware about that, the point groups possible are nothing but to be 10 point groups, and that already we have seen at the beginning of this session is to be there. That 10 point groups are going to be in the two-dimensional cases are to be there. In the two-dimensional, the point groups, possible number of point groups are nothing but to be 10. That is 1, 1m, 2, 2mm, 3, 3m, 4, 4mm, 6, 6mm. These are the 10 point groups possible in the two-dimensional. And if your lattice is going to be formed using these point groups, then and then only such type of the your lattice is nothing but to be called your Bravais lattice. And what two-dimensional Bravais lattice is to be there. And this is what the case where we can see the two-dimensional Bravais lattices are to be there. So what exactly meaning to be as and two Bravais lattices are to be there, and how it looks like to be there? No doubt two-dimensional means there are two vectors are going to be formed. And if you look at the first case where it is to be as an oblique structure is going to be there, crystal structure lattice is going to be formed. If you look at, this is what the vector A is to be there, this is A vector, and this is what the B vector is going to be there. So if suppose this is what the A vector and this is what the B vector is going to be there, and if you look at carefully, this A is not equal to B in this case, and that is what written. This is one vector and this is another vector. There are only two vectors because it is two-dimensional. Along this x, suppose along this is to be y, suppose. So that's why the two vectors are there. It is two-dimensional case. And this is not equal to, this means A vector is not equal to B vector. This length is different for the A vector, length of B is going to be different, and that's why here written A is not equal to B. And again, this angle made by this A and B vector is not equal to 90 degree. And in that case, the such type of the structure or the lattice is going to be formed. It is called to be as an oblique. And this is how represented in this fashion. So if you look at the another one type or the two-dimensional Bravais lattice, second type, there are possible 5 Bravais lattices from the 10 point groups in the two-dimensional case. Now this is what the one another case. If you look at, this is what the A vector is to be there. No doubt, if you see the diagram, it simply gives you the rectangular shape. And that is what, suppose this is what the A vector is to be there, and this is what the B vector is to be there. The A vector is to be longer and the B vector is to be small. And if you join these points, respective points, then you will get the rectangular. But it is called to be as an primitive rectangular case is to be there. And in this case, again, A is not equal to B. But important factor is, for the rectangular case, there is an angle in between the vector is 90, and that is what the case where if you look at here, it should be a, this one is called to be a 90 degree, and that's why it is shown here to be as a 90 degree angle. In the previous oblique structure, the angle was not, A and B is not equal there, but the angle is not equal to 90 there. But here A and B are not equal vectors, but important factor, the angle in between them is 90. And very important case again, as far as this primitive rectangular case is to be there, this A vector is very much long, as far as the B vector is smaller in size is to be there. So this is why it is to be important to show or mention, because if you look at the another two-dimensional Bravais lattice, it is also the part of your rectangular, but this rectangular is called to be as an rectangular centered. Now rectangular center means what? No doubt, rectangular when it becomes, that's the one side is to be larger, another side is to be small, and in front of whatever be the lines are to be there, that should be equal, and all that should have, vectors should have, their angle should have, that should be 90 degree. Now in this case, why it is called to be rectangular center? No doubt, vector A is to be longer one and vector B is to be a little bit smaller. No doubt angle in between them is to be again 90. But here and the previous primitive rectangular case, what is the difference? That A is not too much long in this case. A is little bit shorter as compared to your previous rectangular. No doubt, as to make it rectangular, A should be greater than B. That is there. But it is not too long as good as whatever we have seen in the previous primitive rectangular case is to be there, and that's why it is little bit shorter, and that is what the small difference in between this rectangular primitive and the rectangular center is to be there. And that is what here it is mentioned, that what the exactly A is not equal to B, and the alpha gamma, the angle in between these two vectors are nothing but to be 90 degree, as it is the rectangular. This is what the third type or the Bravais lattice is to be there in the two-dimensional case. Now here is the third. After the third, it is going to be the fourth one. As you are aware about that, it is nothing but to be simply giving you the square, as square is nothing but to be having the equal sides are to be there. That is called to be your square, and that's why here if you look at A and B vectors are going to be having the equal sizes are to be there. Vectors are of equal sizes, then it becomes to be as a square, and the angle in between them is nothing but to be 90, and that's why here if you look at this case, here it is to be written as a part where it is to be as an particularly it is nothing but to be having the rectangular the square is to be having the 90 degree, and both the vectors are going to be the similar and having the equal sizes are to be there. Now the next part, which is to be the last one, that is Bravais lattice in the two-dimensional case, and that is nothing but to be called your last one, hexagonal. If you look at this hexagonal case, in this hexagonal case, what happens? A and B are equal. If you look at this vector, this A vector and the B vector of equal length, but the angle in between them is equal to 120 degree, and that is what it is like this. So either it is having the equal sizes of vectors A and B, two-dimensional, but the angle in between them is 120 degree, and that's why the such type of the unit or the such type of the your hexagonal structure is nothing but to be the part of your Bravais lattice in the two-dimensional case. So these are the what exactly the 5 Bravais lattices as far as the two-dimensional cases are going to be concerned. No doubt it is two-dimensional, that's why there are two vectors, and according to their lengths, different lengths in there and different angles in between them, that 5 types of the your possible Bravais lattices are shown in this case. Now if I want to see in brief what exactly this Bravais lattices relationship is to be there with this your case, where it is called to be as an your basically as an part where this for that I will make this window to be shorter one for very few minutes to understand this case carefully. So look at this case carefully. This is what the complete structure for the Bravais lattices as far as the two-dimensional case is to be there. And in this case, if you look at, this is what the 4 crystal systems. With these 5 Bravais lattices, 4 crystal systems are made as far as the two-dimensional case is to be there. Now which are the Bravais lattices in the two-dimensional? That we have seen oblique, another rectangular primitive, that is to be there, and the rectangular centered, square, and the hexagonal. These are the 1 2 3 4 5 Bravais lattices are possible in the two-dimensional case. But with these 5 types of the Bravais lattices in the two-dimensional, there are only 4 type of the your crystal systems are there, which are that oblique, rectangular, square, and hexagonal. This rectangular is going to be merged. This is centered and primitive. They are merged in this rectangular, and that's why the crystal systems are made, that is to be 4. If you look at examples for this characteristics point groups, as far as oblique contains 1 2, that what type of the point groups we have seen in first at the beginning, that comes for the oblique 1 2 is to be there. For the rectangular primitive it comes 1 m 2 mm. For the your square it is going to be 4 mm. These are the 2 point groups come under this example for the square. And as far as the hexagonal type is going to be concerned, there are possible point groups are symmetries are going to be there. 3 m 6 mm are to be the case. These are the point groups, or the basically symmetry are going to be possible for these Bravais lattices are to be there. And this is what the conventional unit cell, as we are aware about that parallelogram is formed for the oblique, the rectangular should be for rectangular, square is should be for the square, and the 60 degree rhombus for this hexagonal is to be there. And what type of the unit cell, each unit cell we have discussed, the characteristic should have, that is to be also it is given in brief, that is A is not equal to B, and the gamma angle in between them is not equal to 90 as far as oblique is to be concerned. As far as rectangular is going to be concerned, A and B two vectors are not equal, but the angle in between them is 90 degree. As far as the square is going to be concerned, the A is equal to B is possible, that two vectors are equal, and the angle in between them is 90 degree. As far as the last one, the hexagonal is going to be concerned, the A and B vectors are going to be equal, but the angle in between them is 120 degrees to be there. So this is what exactly the two-dimensional your Bravais lattices are going to be there. In this case, whatever be the your Bravais lattices are going to be there, that is also we have seen in detail. And basically what is point group and space groups are also to be there, that is also we have seen in detail. So lastly, what is the important factor in these cases are to be there, I will revise. The symmetry operations are 4 types, that is translation, rotation, reflection, and inversions are to be there. There are number of symmetry operations are possible, either translation, rotation, reflection, and inversion is to be there. But there are possibilities mixed type of the symmetry operations are also there in the crystal structures are possible. Again, the point at which the symmetry operations are going to be followed, that is nothing but to be such type of the group is nothing but to be called your point groups. In the 2-dimensional and the 3-dimensional case is to be there. As far as 2-dimensional case is to be there, there are 10 point groups are possible. As far as 3-dimensional case is to be there, there are 32 point groups are going to be possible. As far as the space group is going to be concerned, the space group is the such a type of the group which not only contains the point which are at a certain the symmetry which is going to be followed at one point, but it also contains all the elements related with that crystal structure is going to be there. And as far as the two-dimensional lattices are going to be concerned, there are number of possible point groups are 17 in the 2-dimensional case, and the number of space groups are to be possible. And as far as the 3-dimensional case is to be there, the possible number of space groups are 230 is going to be there. But as far as the Bravais lattices are going to be concerned, the whatever be the lattice which is going to be followed, which consistent with the your point group, that type of the lattices are nothing but to be called your Bravais lattices, either in the 2-dimensional and the 3-dimensional. Now in brief, we are aware about that the number of point groups possible in the 2-dimensional 10, number of space group possible in the 2-dimensional, that is 17, and the number of Bravais lattices possible in the 2-dimensional, that is 5, and the number of crystal systems are possible in the 2-dimensional, that is 4. As far as the 3-dimensional case is to be there, the point groups are 32, the space groups are 230, and the Bravais lattices are 14, and the crystal systems are 7 is going to be there. So this is all about what exactly meaning to be as an point group, space group, and lattices, types of the lattices are to be there. Today we have just discussed about the 2-dimensional case. In the next lecture we will discuss about the 3-dimensional case. Till then, from my side, thank you very much. Be at home and be safe. Thank you.